There we go. Okay. So today we're going to talk about solving an equation. Solving equations. So this is an introduction to solving equations. Really a foundational, important tool, an important skill to have in algebra. Everything that we learn this year pivots around understanding these. That's how important this is. So listen well, and I think you're going to be surprised at how simple it is, because I'm actually going to show you a way in which you can do this. Even a third grader could do this. I mean, it's quite remarkable when you understand what this is really about. And a lot of times it's not taught in a way that allows you to understand that. You just sort of eventually learn it through osmosis. But I think you're going to find this very interesting. The first thing you have to understand is the word equation. What is equation? What's an equation? Yeah, Sal.
It's like anything that has like a plus symbol or like a minus symbol or like a symbol.
Okay, you're almost right. It is anything that has a certain kind of a symbol. What did somebody else said something? Equal. It has an equal sign. Notice that first part of this word, equal, right? So an equation always has an equal sign. What is it called when it doesn't have an equal sign? Anybody know? Amy?
Expression.
An expression, right? So if I say 2x plus 3, that's an expression. If I said 5 minus 7, that's an expression. If I say 2x plus 3 equals 1, that's an equation. It has an equal sign. That's the main thing. Yes?
What if you have like 4 times 6 equals, and then you don't have an answer?
You have 4 times 6, and you don't have an equal sign. You mean with an equal sign?
You have the sign, but it doesn't have an answer.
Well, in a way, that is an equation if that blank space on the other side of the equal sign is considered a blank space waiting for an answer, right?
Yeah.
So, because you could consider that blank space could be like an X, or it could be a question mark, or it could be a box. When you in third grade, instead of using X's and Y's and stuff, you did, like, I don't remember what you said, 6 times 4 equals, and then they put a little box there.
Yeah.
Well, that's algebra. And that is basically setting up an equation, right? That's your variable. Instead of, in algebra though, instead of using a box or a question mark, we're using X or Y or Z. Yes, Tess?
What about like greater than and less than?
Greater than and less than would no longer be called an equation. It would be called an inequation or inequality. Meaning it doesn't equal, but it's greater than or less than. Sometimes they're greater than or equal to, so it's sort of a combo. And when it's greater than or equal to, it's still considered an inequality, but it really is technically an equation and an inequality combined. Okay, see what I'm saying? They're two things in one. Yeah. Right? Okay, so, all right, so we figured out that an equation has an equal sign. There we go. This is like key. An equal sign. What does equals mean? What does it mean? Sal. They have the same value. Do you guys agree with that? On either side. If it says equals, whatever's over here must be exactly the same thing as over there. Okay, what else? Anybody else? Anybody else have other ideas or other definitions of an equal sign? Yeah?
The same.
Yeah, totally the same. That means this side is exactly the same thing as this side. Exactly. Now, what if they don't look the same, though? Is that a problem?
No.
Well, let's do something simple. Let's say we have 1/2 equals 2/4. Is that okay? They don't look the same. But they equal the same, right? Because we know our fractions. We know that this pizza has 2 pieces. It's cut into halves, right? And 1/2 is a half. This one's cut into 4 pieces, but we're having 2 pieces, which turns out to be half of the pizza. So really, they're the same thing. They don't look the same, but they are exactly the same thing. In order to have an equal sign, they have to be exactly the same thing. Yes?
Besides, if you divided like each of those by 2, you get 1/2.
If you
Like
divide...
if you divide 2/4 by like 2, you'd get 1/2. So
If you divided 2/4 by 2,
like 2 divided by 2 is 1, 4 divided by 2 is 2. So technically it is That's another way of making sure.
Okay. All right. So what I was going to say, so if this is the case, equals, whatever equals means that basically, you guys said the value on the left is the value on the left is exactly the same value on the right. That may not be the best English, but that's okay. It's short and sweet. It makes sense, right? Okay. Anybody have an idea what this is? Let me see if that can be seen. Yeah. Yes, Liam. It is a scale. Why on earth would I bring out a scale to talk about equations?
To measure 1/2.
Serena.
Because if you have, like on the saying, if it says the value on the left is exactly the same as the value on the right, and you have on the scale you have like the left side and the right side.
Right.
If you put more, if you have a value on the left side that is greater than the value on the right, it's gonna be like.
Right. Like if I had something, let's just do something. Let's just get something out right now. All right. Let's just get our stuff out. All right. We have all this cool stuff. This is really cool, you guys. Where do you see this? All right. Let's say I put 5. I got a 5, right? And I'm going to put it on this side, on your right side, right? Oh shoot! What's going on? Look, it's perfectly balanced. That's great. Oh! I don't get it. Okay, wait. It's probably because I should have put it on this side. So I'm going to put this. Oh shoot! What's going on? Wait a minute. What do I need to do to make it stay balanced? What is? Do I have an equal sign there? Look at that. My balance thing has an equal sign. This is an equal sign right here. So if I'm going to put 5 on one side, I darn well better put 5 on the other side. Now if I do them one at a time, it's not going to work, right? I got to do them together, right? So really, really carefully. I'm getting nervous. Ah! It worked! Look, it's perfectly balanced. Oh my gosh, that's amazing. Now, what if I want to add a 3 to it? If I add a 3 to this, oh shoot. Oh my gosh, this is really kind of a bummer. Let me think. I'll put my 5s back on, 5 back on. Okay, I want to add a 3, but in order to add a 3 to this side, I am going to have to do the same thing to the other side. 3, 3. And it stays balanced, perfectly balanced, right? Now this is obvious, am I right? I mean, this is really obvious, right? It gets better, okay? It gets less obvious, and it gets really cool. All right, so let's say, instead of that, I have this little green thing, right? My little green thing. Now, I don't know what this is about. I don't know what the value of this little green thing is.
Symbolizes a variable, right?
I have no idea what this thing is, and so Nathan, you were right on. This symbolizes a variable. All right, so we're going to call this little green guy X. Okay? Now, I am going to put these two on at the same time because I know what happens if I do them separately. Oh my gosh! It's completely level. Look at this. What do I know about this unknown variable X, Indu?
That's plus 5.
It equals 5. Why? How could? But it's a green tube, right? It's a green thingamajigger. This is a 5. How do you know this is 5?
It says so.
It's not tipping.
Because it says so, right? Because the balance is balanced. It's totally balanced. This has got to be. Oops. That has got to be a 5 because it keeps this balance in balance, right? So when I write X, I should probably use the black one, right? Where's the black one? when I write x equals 5, I know that the value of x is 5, right? I know that. Okay, let's make it a little harder. Let's say I had, let's see, where is one of those guys? Okay, we'll do this. Okay, let's say I have these two unknowns, two x's, right? They're always going to symbolize the same variable. So like I'm going to call them x's. So they've got to be the same value. I mean, this x has to equal this x. But I don't know what they're going to be because they're unknowns. And I'm going to put them on the same scale on the opposite sides of a 10. And it's balanced! So the question is, this means 1x plus 1x is equal to 10.
So x still equals 5.
2x.
So, really, how many x's do I have?
2.
I have 2 x's, and 2x is equal to 10. What do one of those x's equal?
5.
5. Let's try. 5 plus 5 is 10. 10 equals 10. You're right. So that's pretty easy, right? So that's interesting. So we just, what am I doing? So we just figured out that 2 x's, which is, actually, let me just write it this way first. We have x plus x is equal to 5, right? So 2 x's is equal to 5. I mean, sorry, 10, sorry. I was looking at that. Let's get rid of that. Okay, so 2x is equal to 10. And we figured out, just by knowing our math, adding and subtracting and stuff, we figured out that 5 plus 5 is equal to 10. So x has to be 10. Now, x has to be 5. Now look what we can also do. When this is the same thing as this. Does everybody know that?
Yeah.
This means 2 x's. In other words, x plus x, not x times x. What would it be if it was x times x? How would I write this? X squared. Exactly. X squared. This is 2x means I have 2 x's and they're being added together. And that equals 10. So if I can write it like this, what is the 2 doing to the x? Multiplying. So I could actually undo this. Like, remember that little thing I taught at one point? Like, last night x was all by itself and somebody came in and they multiplied that x by 2. And I'm going to undo that. So I got to do the reverse. I've got to divide by 2. That's the reverse of multiply, right? Divide by 2. Divide by 2. X is equal to 5. All right? Getting it? Okay. Now we're going to make it hard. Okay? Yeah. Let's say I have, and I'm going to put them on, pretend I've got this on a lock or something so it doesn't move for a second. Because I can't do it. We're going to do 4 here and 9 here. All right. So I have suddenly 3 x's on this side plus a 4. So x plus x plus x plus 4 is equal to x plus x plus 9. Now that's a fairly complex problem. That's actually rather complicated. But we learned something. Remember when I had a 5 on this side and I had a 5 on this side?
And because x's are 5s.
We learned something. Remember we had a 5 on both sides, and I wanted to add a 3 to both sides. I wanted to add a 3 to this side, but when I added it just to this side, it went out of balance. So I found I had to add a 3 to both sides, right? So I have created a rule, and this rule is like so important. This rule says it's the golden rule of algebra. The golden rule of algebra. Do unto one side of the equation. Yeah.
It's just arcane.
That's the old language. That's this one. Do unto one side of the equation exactly as you would do unto the other. That's the golden rule of algebra. And I've seen it written different ways. You can use your own words. Do unto one side of the equation exactly as you would do unto the other. Right? I've also seen it written like this. You can do anything you want to one side of the equation, as long as you're fair and you do exactly the same thing to the other side. And it will maintain its equality. It'll maintain its balance. As long as you do the exact same thing to both sides, it'll always stay balanced. It may change the numbers, but it will always stay equal. Right? Does that make sense? Okay, so now we got this complex problem that I don't know the answer to this right off the top of my head.
I know it.
And
I know.
I could figure it out, and some of you have figured it out. But let's use the golden rule of algebra to do this. I want to simplify this, and I realize this is not very simple yet. I want to simplify it. I see that there's an x here and there's an x here. I want to simplify the board. I want to clear off what I can. Could I take this x off? If I take this off, what's going to happen? It's going to go out of balance, right? It's going to go, right? And everything's going to fall off. I'm not going to do that because I don't want to have to set it up again, right? But what if I want to take this off? What would I have to do to make it not go off balance?
Take one off the other side.
Take one off the other side. So this is legal, right? I can take one of each. Oh my God, that's amazing. Look at that. We just simplified this problem. Oh, wait a minute. There's another. On this side there's an x, and on this side there are a couple x's. I could take an x from each side again. Do you agree with me?
Yes.
Okay, here we go. And it's still in balance. Oh my gosh, that's amazing. So suddenly I have this equation that is a lot easier for me to figure out really quickly, right? I see that something plus 4 is equal to 9. What's that something?
4x.
5, right? 5 plus 4 is 9. So then I know it's going to work. And I could even try it again. I could go back up. I could put these back up. We said x was 5, right? And we said, what did I have on here?
2 of 2.
I had 2 of these over here. We could try it. We could do what's called a check, right? So we said that x was 5. Let's try it. 5 plus 5 is,
10.
plus 5 is,
15.
plus 4 is,
19.
okay, 19. What's 5? Plus 5 is,
10.
plus 9 is,
19.
19 equals 19 to checks, right? That's amazing, right? That's totally amazing. So we can solve complex problems just using a scale by simplifying, by following the golden rule of algebra. So let's do a complex one. Let's do something like this. We'll do all these to make it
Oh yeah.
right, and we'll say 1, 2, 3, 4, 5. We'll do 3 over here, and we'll use different numbers. We'll say plus 6, and we'll say, what did I do with my 10? You see my 10? I'll do that. All right. So I now have, and if I were going to write this on the board, what would it be?
Plus 6.
1, 2, 3, 4, 5.
6x.
So how would I do that? I would do 5x. This is what that says. 5x plus what?
6.
6 is equal to what?
3x plus 10.
3x plus 10. Now that's a complex algebraic equation. Now some of you know how to solve it. Actually, now all of you know how to solve it. You can always use a scale to solve it. So we've got that up here. There are ways to do it algebraically, but I want you to see when we do it algebraically, we're doing exactly the same thing that we're doing when we do it with the scale. We just might use a shortcut here and there. But notice, okay, I see I could take one of each, right? Okay, it's still in balance. I could take another one of each. Great. It's still in balance. I could take another one of each. It's still in balance. It's awesome. Wow, I just made this a lot easier, right? So I have 2x's plus 6 is equal to 10. Now, I just figured out, because of the golden rule of algebra, I could actually simplify this even further. Because I want to know what my x's are, right? I don't want to know what 2x plus 6 is. I want to know what x is. Does that make sense?
Yeah.
And I want to get rid of this 6. But if I get rid of this 6, you know what's going to happen, don't you? It's going to go like that. So but I want to get rid of this 6. What could I do to get rid of the 6? Adam. I got to take 6 away from both sides, right? So 10 is the same as, well, okay, let's see. 10 is the same as, do I have another 6 in here? 10 is the same as 6 plus 4, right? I'm going to just do that for now. Replace it. 6 plus 4. So I could take a 6 away from both sides, right? And it'll still stay in balance. Because I didn't do anything wrong. I didn't do anything illegal. I followed the golden rule of algebra. I did exactly the same thing to both sides. So I now know that x plus x is equal to 4. So what does x have to be? Liam. 2. So we had that very complex problem when we figured out just very quickly with the scale that x is equal to 2. That's pretty amazing, right? Pretty amazing. I can even make these harder. Let's try a different one. Let's try another one. Let's say we do why don't we do 8x plus 2 is equal to 4x plus, let me think about this for a second. 8x plus 2 is equal to 4x plus 10. Hopefully that's going to be a even number for, hang on 1 second. Yeah, I think that'll work. Okay, so hopefully I'm right. So we've got 8 x's, 1, 2, 3, 4, 5, 6, 7, 8. And then plus what? Plus 2. Where's my 2? Boom. You what? Oh, sorry. It's because I have magical powers. I'm keeping it balanced just for a moment, right? And then I have 4x plus 10. Where's my 10? There's my 10. And 4 x's. Here's my 4 x's. Well, 3 x's. Okay. So I have 4 x's plus 10. So now I'm going to do something that we do in algebra that is actually a shortcut. Instead of taking one of each, right, which I know I can do, I've done it several times, right? I know I could take one of each, and it stays in balance, right? But look, I notice, that's interesting, I notice that on my side with the smaller number of x's, how many x's do I have? 4. So maybe in one move, I could take 4 x's away from both sides. Do you think so? Mm-hmm. Let's try it. I'm going to take 4 away. Wish me luck. It worked. Okay, it worked. And it stayed in balance. Wow, I just simplified this. Now, this is interesting. I have my x's here, but I have this doggone 2. And I don't want it there. So I'm going to take it away. But in order to take it away, I have to take 2 away from this side too, right? So I'm going to, when I take 2 away from 10, what am I going to have?
8.
All right, so here we go. Watch this. This is amazing. Look at that. I took 2 away from both sides. I now have 4x is equal to 8. So let's write that down for just a second. We just figured out that 4x's equals 8. That means x plus x plus x plus x equals 8. What does x have to equal? Kareem, you're right on. 2. So you could figure it out. You could say 2 plus 2 plus 2 plus 2 is 8, right? So it works. Or you could say 4 times x is 8. And what's the opposite of times? So I could go divide by 4. Divide by 4. Look at that. What does 4 over 4 equal? 1, right? So now I have 1x is equal to 2. X is equal to 2. So this thing works really, really well. Now I'm going to make it harder, okay? We're going to definitely make, does it make sense?
Yeah.
Can I erase this? Is that okay?
Yeah.
All right. I'm going to make it harder. All right. What if I gave you something like this? 2 times parentheses x plus 1, why not? And then we'll say, let me think, equals x plus 8. Let's try that. All right, how could I do that on this scale? Does anybody have an idea? We have to understand what this means. Yes, Sal, what would you think?
Use the distributive property 2x plus 2.
You could. Remember the distributive property? Remember the elephant nose, right? You got the 2 times the x and the 2 times the 1, right? And it becomes 2x plus 2. I could do that. But, and then I could put it on the board, right? Or I could do something else. I could say, well, PEMDAS says to go with the inside the parentheses first. So inside the parentheses, I have an x plus 1. So I'm going to put an x plus 1. X plus 1. Boom, right? So there's my x plus 1. Well, I'll put it here. X plus 1. But what does this 2 mean? It's 2 times. So how many x plus 1s do I actually have? I actually have 2 x plus 1s. Does that make sense? That says I have 2 of these. All right, but I only have 1 of them up here, so I got to put another one. So I'm going to put another one. X plus 1. Boom.
It's so patterned.
X plus 1.
So patterned.
Oh, wait, and it's, yeah. Okay, equals x plus 8. We got to do x plus 8. X plus, thank you. X plus 8.
Good eye.
So now, we've taken this, actually, this is even more complex than the previous ones I've given you. And yet, it doesn't actually look so bad when we put it on the scale, right? We realize, oh, I could take one of these away from both sides, right? And I realized, oh, this is 1 plus 1 is 2. I could take 2 away from this and 2 away from 8. What would I get if I took 2 away from 8? 6, right? So let's get our 6 out here. If you guys see these numbers, feel free to find them from, okay. All right, so I'm going to take 2 away from both sides, and so all I have, x is equal to 6. So the answer to this problem is x equals 6. All right, does that make sense? See what I mean? So you see how the scale works? I mean, that's what an equation is. It's merely using a scale to keep it in balance at all times. And you've got to use the golden rule at all times. Now the question is, how do you do it without a scale? Right? So when we do it in algebra, it's the same thing. Now, if I wanted to do this way, I could say, well, 2 times x plus 1, I could say x plus 1 plus x plus 1 equals x plus 8. I could do it that way. I think it would be easier to use distributive property like Sal had suggested. But I could do it this way. And I could notice I have like terms now. Remember like terms? You guys learned those. If something has an x in it and a number next to it, that's a like term, right? What's the number in front of the x? No. What's the number in front of the x? 1. Yeah, it seems like 0, right? Seems like 0, and I know you knew that. I know you knew that. It's just that it's so easy to say, oh, it's 0 because there's nothing there. But it's 1. There's always an invisible 1 in front of every variable, right? Unless there's another number in front of that variable, right? So that's 1x plus 1x. But how many x's do I have? I've got these 2. How many x's do I have? 2 x's, right? So I could do that, right? Actually, I don't even have to do that. Let's just go back. Let's forget that. Let's just do it this way for a second. I'm sorry, I'm simplifying. I'm just keeping this simple. X plus 1 plus x plus 1. Look, here's my scale. I see I have an x on this side and an x on this side. I could cross them out. I'm going to use a different color because it makes it easier for me to see. I'm going to cross out 1x from both sides. That's awesome. And then I have, so all I have left now is I have x plus, what's 1 plus 1? 2. So I could do x plus 2 is equal to 8. And somebody, this is really disturbing because last night x was all by itself. I checked before I went to bed. I came over here, right? I checked. And doggone it, I came in this morning and somebody had added 2 to my x. And I am so pissed, right? So I am so disappointed. Excuse me. All right. So somebody added 2 to my x, right? And so I am going to subtract. I'm going to undo that adding 2. So I'm going to subtract 2 from this side, and I'm going to subtract 2 from this side, and I've got x is equal to 6. Oh my gosh. It works. It works. It works. Isn't that cool? It is really cool. It really works. Okay, so we're basically done with the scale, but I want to try doing a few problems now on the board, so you guys start to. And then, do you guys want to? Does people want to try the scale? Do you want me to put problems on the board? What? All right. So I guess I'll end the video for now.
We're not capable of paparazzi.